Alrighty, welcome to Engineering Basics Week 9, or Part 9 I should say. It's been more than 9 weeks. It is hot as balls today, so we're going to make this short and sweet, but it's still going to be fun. Everyone see the stream? Good? I need audio, I'm not watching Discord. Awesome, alright. Oh yeah, it's hot. So, last time, week 8, or number 8, whatever. Last time, we talked about frames, machines, and trusses. We discussed what they are, who they are, and where you might see them. Today, we're going to start learning about how to design them, how to make them, how to figure out what we do with more complicated static structures. So, before we move on to that, can anyone tell me what is stress? And yes, I will sit here silent until I get an answer. A force applied over an area equals a stress. Perfect. Now, can you tell me in non-mathematical words what a stress is? What is stress? Not a stress. Anyone want to try? Well, there is such a thing as bending stress. Bending stress is equal to PV over RA. Oh wait, no, that is totally not bending stress. Bending stress is equal to MC over I, but that is not the definition that I'm looking for. That is not an English definition of stress. If no one knows it, that's fair. We actually had this question amongst my roommates and I, who are all 3rd and 4th year MEs, and we had a really hard time actually answering that question. So for now, until everyone gets a good grasp of what it means to what stress actually is, you can just think of it as some mathematical thing that we use to talk about materials, right? It's the amount of force that we put on a material for a given area of said material. And again, this is just review for those of you that might not have seen the earlier weeks of Engineering Basics. So, to that end, can anyone tell me what is strain? Any takers? So, alright, so I've got a force. Yeah, there you go. Change in length over initial length is the equivalent of strain. You got the math definition. Can you give me the word definition? This one should be a little easier to provide a word definition for. Yeah, that's a pretty good definition. So yeah, that's exactly right. When we measure strain as the amount that a material deforms compared to how big it started, right? That way we can use strain to talk about all types of materials and all types of sizes of things, and we can compare them at more apples to apples. So now let's get back to what we talked about last week. So we introduced the idea of all these different types of structures. So a truss is just a structure made up of multiple members. A lot of times people say that a truss is a structure made of 2 force members. So something like that would be a truss structure. You can almost always recognize a truss structure because it looks like a bridge. Our chassis is technically a 3-dimensional truss structure. Right, if you're to look on the back here, and let's get a color that'll show up there. If you look on the back here, right, we've got multiple members. They're all joined together. And a lot of these members only experience force in 2 directions, right? So these these members here only see force from either side. And a two force member would be some sort of beam or tube or some member that only experiences tension or compression, right? If we look at this picture, we've got some 3-force members, well, technically 3 plus force members, right? This little section right here, where all the suspension links come on, right? It puts forces. If we were to look back at this picture, right? It's not just in tension compression. It also puts forces on our beam in weird places. One other thing that I didn't necessarily directly mention last time is typically when we're talking about truss or frame structures, we're talking about things that are pinned at joints. So the reason that we do that is we want to say that there's no moment that can happen, right? There's no possibility for these to be put in bending at the end of whatever your machine or whatever your structure is. In reality, usually that's not the case, right? Most bridges aren't bolted by a single bolt at all the connections, right? There's a whole string of bolts. And also, a lot of structures like the Baja car are just welded joints, right? There's something maybe like that. But the bending that we see at these joints is comparatively negligible to the tension or compression. So, even though technically this wouldn't be made of 2-force members because they can experience moments down the corners here, it's more or less a truss structure. A big thing to remember just about engineering in general is this is an applied science. So any of our definitions, no matter how rigid we try to have them, right, we're always making assumptions. We're always doing the best. We're using models to describe what we can. That's why we use safety factors. That's why we have different ratings. It's not that this is exactly the way it is, period. So in the case of a bridge or of the chassis on the Baja car, usually considering it a truss structure is pretty applicable. So we went over trusses. We said what members are. Frames, I guess if you were to continue going through this definition, a chassis with suspension attached to it is more like a frame because there's it turns into components that have at least 3-force members. And you could also consider the whole Baja car. So if we put the chassis in the context of the whole car, it would be a machine because the whole thing the whole purpose of it is to do work. So to do work means we're moving something, right? If you think about a bridge, we just think about a regular old bridge that cars drive over. Sure, it does work in that it resists forces from cars, but really its whole purpose is to stay there and not move. We want it to be pretty damn static. So where we're going for today, we're going to start talking about the method of joints, which is some method of learning how we can talk about and do engineering on truss structures without them moving. Technically, we can use the method of joints on machines, right? We can use methods of sections and method of joints together, interchangeably, separately on frames, machines, and trusses. But some of them are more useful, using one or the other in certain situations is more useful. For something like this bike, if you guys, especially those of you that are new to Cal Poly, if you guys are interested in biking, downhill, mountain biking, that kind of thing, you should check out Cal Poly Bike Builders. I don't know what they're necessarily up to this year, but last year, I think this might be the one from 2019. But they actually build this bike. Oh no, this is, this I think is the one from 2019. But this is a titanium frame that they actually designed, welded together, did all the engineering on. And this guy, Fedor, he's pretty sweet. He's a shop tech. So we know what it's for. We know you can use them together. So how do you actually do the method of joints? So there are 4 general steps to the method of joints. And these are going to be pretty similar for the method of sections and method of joints, but you can kind of think of it like solving a whole bunch of statics problems one after the other. So first thing we need to do is determine the external equilibrium. So if we go to our general our bridge of science example, right? So we have our bridge of science, and I want to figure out what the tension is going to be in this beam right here, in this member. The reason I want to do that, I want to figure out what size I-beam I need to use. Something like that. In order to do that, well, I need to know what the loads are actually going to be seen. What's actually going to happen to this bridge. In civil engineering, they have a whole big they have a bunch of classes about exactly what safety factors to use, what conditions to design for. Generally speaking, though, for the method of joints, you want to figure out what your worst case loading condition is. So that means the highest forces on your structure. And actually, I'm gonna draw this here. We'll just say that we have a snow load, right? So we've got I don't know, we'll call this 50 pounds and 50 pounds. For a bridge, probably not a very big snow load, but I don't know, could be a footbridge. So first thing we need to do is determine our external equilibrium. So we need to figure out how does this bridge interact with its environment before we can figure out, before we can determine what the different interactions here are. Because if you think about it, if this wasn't pinned, right, if this was maybe a sliding joint, or if this joint here was something else, then it might just be that the bridge moves, right? If it's not attached at one of the abutments, you're going to go right into the water down here. So we need to figure out what our reactions are on both, on anything external to our problem. For this one, pretty easy. I mean, I didn't put any dimensions on here, but I think we can all see by eye this is going to be pretty even. So 50 pounds and 50 pounds. So now we have everything external to our structure. Next, we want to separate the members at each of the joints. The whole idea of the method of joints is that every joint is a bolt that has a whole bunch of different forces on that bolt. But all the forces have to be equal to 0, right? If the forces aren't, if the sum, let me write this down here in math speak. If the sum of your forces is not equal to 0, that is the same thing as saying you have some positive acceleration. I mean, your mass could be equal to 0 in order to satisfy this, but we'll use real world physics. So real world physics means engineering. That means that your acceleration is positive, or at least non-zero. And if you're accelerating, that means you're not static. You're not moving, right? These are truss structures that we're mostly dealing with here. We don't want them to move. Moving bridges are bad. Besides the whole, like, temperature thing. Details for later on. So we want to picture, I'm just going to take this joint right here, for example. So on this joint, I'm going to separate all the members. I've got one member here that goes into that joint, one member there that goes into that joint, and one member here that goes into that joint. And I also have this force. So we've got a 50-pound force there. 50 pounds. Now I want to do statics on this joint. So the big assumption that we make in statics is that everything is rigid. Typically with most engineering, at least introductory level engineering applications, you first assume that all your members are rigid, and then you do some mechanics and materials afterwards to figure out how they're going to deform. In general, right, if I have a good bridge and I put 50 pounds on the top corner of the bridge, it's not going to move. Sure, that 50 pounds is going to be distributed into the members, and they're going to flex ever so minusculely, right? But by and large, they're not going to move, and we can treat them as such. So if this has to stay in its position, then we know that it has to impart some reaction force in this direction. So we're going to turn this right where this pin is. We're going to turn that into a free body diagram. I'm going to go to the next, make a new page here. So we've got pin, got one beam. We're going to say that we're just looking at this beam. That we've got beams in every direction, and we've got our We've got our 50-pound force. 50-pound force. So this beam we know can only exert a force in this direction, so we have to have a force there. This beam we also know can only exert a force in this direction, and this beam we know can only exert a force in this direction. And one of the nice things about our assumption here, let me draw this more in 3 dimensions. So I'm just gonna assume we have a nice long pin, and that's this pin here is what I'm talking about. I've got one member that kind of comes off of it like that. One member kind of comes off of it like that, and then another member comes off the end here. And we can see on this pin that if I put a force going straight down, it must be constrained by all of these beams, and because we're assuming it's static, it has to be in that direction, right? If it's not in that direction, let's say if this beam were to resist in this direction, well, that means we're suddenly putting a moment on this beam. So we're going to try and rotate that beam, right? Because if I draw this, imagining we remove this beam real quick, do our own free body diagram on that. If we're putting some force, let's say we have a force that way on the pin, that means we have to have an equal and opposite force on the beam here, and that's going to start to rotate this beam. Now we know that this beam can't rotate; it has to be only in tension or compression. And I hope that's at least kind of clear. Typically this topic is something that you introduce over multiple weeks in statics. For those of you that haven't taken statics yet, that's ME 212. I think all of the engineering majors, including like Archi and bioengineering, I think they all have to take statics. And even some of the business students will also take statics. But yeah, once you get to a statics class, this will hopefully be explained more mathematically. But I think everyone can kind of get the picture that, okay, these things have to happen in this way. So that being the case, assuming everyone understands that. Oh, and by the way, I didn't say this at the beginning, but if you ever have questions, I talk fast and I want to get through examples, but this is an open forum. If you have questions, just ask them. I'm not watching Discord, so you'll have to use audio or try and get someone else to use audio to ask said questions. But yeah, feel free to ask if you ever don't understand something. I think I don't remember what there's some business concentration. Maybe it's what is it? I don't remember what the concentration is. I don't know. I know in my statics class there was one business major, and maybe it was just that he wanted to. Yeah, that one would make sense. Is that in the business college? Okay, yeah, maybe that's what it was. Yeah. All right, see you, Liam. Okay, so back to our free body diagram. Now that we can have kind of sketched this out, in order to make a proper free body diagram, Mello would have my head if I didn't first put some coordinate axes on here. So we've got X and Y. We've got our pin. And then I'm gonna draw this green force in blue because I drew the other ones there. We've got 50 pounds here, and then we've got 3 unknown reaction forces. And even though I'm drawing these as being in compression, right? I'm drawing them towards the pin. Really, once we solve this, they could go any direction. It would just end up being a negative value. So if I draw it in compression and I get a negative value, it would actually be in tension. I like to, if it's a really complicated problem, just draw everything in tension and then solve for it later. If it's a problem like this, right, we can pretty much tell, well, we're pushing down, so these are all going to try to push back. So they'll probably be compressive forces. So now that we have our forces here, we can say, we know from statics, we know the sum of the forces in x is equal to 0, the sum of the forces in y is equal to 0, and the sum of the moments is equal to 0. For truss structures, right, because we're solving at all the pins are one-dimensional. We assume pins are one-dimensional, so they don't rotate, which means we don't have to worry about solving for our moments, which is kind of nice. So this just leaves us with solving for forces in x and y. I'm going to label these real quick, A, B, and C. So they've got some angle, right? Angle alpha, angle beta. Oh, that's not a beta. Angle beta, and this is, I don't know, we'll call it horizontal with the x. So if I do sum of the forces in x equals minus c, because right, we're going x, that's in the negative direction, plus a, would that be cosine? Oh, not cosine. It's gonna be a sine alpha. Right? If we're going for sine, that's the opposite of the hypotenuse, so that'll give us that leg of this force, right? So that's the leg that acts in the x direction. And then plus, or I guess minus, b sine beta, because, right, this is b, it's acting in the negative x direction to a little bit, and then to get that component of the force, we treat it in that direction. So now we have one equation with 1, 2, 3 unknowns, right? I'm assuming beta and alpha are given. So then we can do the sum of forces in the y direction. We'll get a similar thing. Oh, whoops. I messed up here a little bit. C does not act in the x direction. There we go. Back down to 2 unknowns. Nice. All right, so in the y direction, we know that this is going to be minus c, oh dear, minus c plus a cosine alpha plus b cosine beta, and c doesn't act. Oh, that's where c came from, right? Minus c. This is our 50-pound force. My bad. This is the 50-pound force. So now I have 2 equations, but I still have 3 unknowns, which normally we would say, oh shit, that's not how algebra works. I'm still going to have 1 unknown. But the beauty of the method of joints is now we can just move on to the next joint. And we can do that in order to get another set of equations that are local. Let's say we take the joint down here. So this joint would have some forces, maybe that direction and that direction. And we also already solved for the reaction with the ground. We got that force. And this one, we've only got 2 unknown forces. So for this one, we actually know that we'll be able to solve all the statics on that pin, which will tell us, because this is equal and opposite to that, we can solve for, what did I call this one? Force A, which means that then we can then solve for force B and force C, because that'll take care of some of our other unknowns. So let's go ahead and learn by doing. Woohoo! Normally in engineering basics, I try and find a Baja or racing or otherwise non-school related example. But for the method of joints, it's really most applicable to bridges and stuff. Bridges, trusses, structures that look like this. So we're just going to do some regular old basic ones like this. That way you'll know what it is, you'll know how to use it, and we can move on. So, any questions before we start? So we went step 1, determine the equilibrium. Step 2, separate the members of the joints. Step 3, perform statics on each joint. And then step 4 is walk through the structure until we figure out what we want to know. Any questions before we start working on this example? No? All right, and let's go for it. So I said step 1 is solve for external forces. I really need to change how this reads my handwriting, because that is atrocious. I probably just make it pressure sensitive. All right, so solve for external forces. So this structure, ADECB, structure, I'm just going to call it structure. What's a good name for a structure? Anyone have a good structure name? We'll make it, sure, structure 1, nice and easy. Make it match our example. So for structure 1, let's draw our free body diagram. And because all the internals are rigid here, I'm just going to draw the external members and call it a day. So we've got a pin joint there. We've got a slider here. And we've got some known forces. So we've got, this is 5K, this one is 10K, and this one is also 10K. And then we also have some dimensions. So there we have 10 feet, and then we've got 12 and 12. All right, that one's too thin. So now we just do basic statics. So I'm actually going to, let's see if I can do this the easy way. Let's copy you, add a page, and paste you. Ooh, and can I increase your size easily? Is that a thing? Maybe not. Whatever, that's fine. All right, I'm just gonna move the, oh dear. Gonna take this and we're gonna move it over here. So that's our problem. So time for a free body diagram. Always start any free body diagram ever with coordinates. So I'm gonna call this my x direction, gonna call this my y direction. And I think it makes a lot of sense to go ahead and put this corner here, I think that was corner A, down in the bottom there. And I think it also makes sense, if we look back at our problem, to line this up, line up our axes there. So we've got X, and we got Y. So I'm gonna draw the structure in black here. One nice thing that you guys will discover in doing engineering problems is it is very convenient to separate your structure, or to separate your free body diagrams by color. And I know that sounds like a artsy, fruity, you know, it's not pen and paper kind of thing, but it does make it really, it helps dramatically. So it's amazing how much it helps to keep stuff together in your head. Anyway, I'll get off my soapbox now. So I have one force A down here. I have another force, I believe this is B, and I have a force C, right? I label this correctly, A, B, C, cool. Then I have a reaction force here. And some people, it doesn't matter what direction you draw your unknown forces in, right? Because we're just going to solve them or whatever. If they're unknown, I think it makes a lot of sense to just draw them in the positive direction, and that way we can figure them out in the negative direction. Or if they come out to be negative, kind of like how I said earlier, then we just know they're in the negative direction. So because this is a pinned joint can have two reactions, so two perpendicular reactions. I'm going to call this dx and dy, and know that in reality on this pin there's going to be one reaction force that's at some angle, right? And there's a y component to it and an x component to it. For doing statics, right, at the end of the day, I don't really care what the reaction force is, but I do care about what the components are because I want to figure out what the tensions are in all of the other members. So I think it's fine to just leave them separated for now. Depending on the problem, right, you might need to know what size do I make this bolt, so then you do want to know what the total force is. Reality, doesn't matter. So we've got reaction dy and reaction dx, and then we've got a slider here. So the way you treat sliders is they can resist in the normal direction. So I drew this slider like this, which means it's free to move this way and that way. So there's no reaction there, but I can't push it into the wall anymore. I hope that kind of makes sense. One thing you will have to get used to in engineering is figuring out what the diagrams mean. But these are kind of the two external conditions you'll see most often, is a pin and a slider. So I know my slider can only resist in one direction, so that's in the x direction. And this is called reaction A. So I'm just going to say that this is a positive force, because then I can figure it out later if I need to, at A. Call it RA, because I already have a force labeled A, so we'll just call this RA and be done with it. So now I do my regular old statics. And some of you are probably ahead of me and have already figured out all of your statics equations. And if anyone has done so, feel free to chime in. And the sum of the moments equal to 0, 0, 0. If not, I'm just going to start with the sum of the forces in the y direction. So we know that this means dy. I'm going to start with the forces in y. So dy minus a minus b minus c equals 0. In the x direction, we've got positive dx plus positive RA equals 0. And for moments, I can take the moment about any point on here, but I have 3 unknowns, so there's probably going to be some real convenient way to figure out what point I want to take the moments around. So if I do the moments around point D, then that means I have 1, 2, 3, 4 forces to deal with, but 3 of them are known, so that's like an equation for free. If I do the sum of the moments around RA, then I get 1, 2, 3, well, then we're down to 3 forces, and 2 of them are known, so we also get dx for free. If I take the sum of the moments about here, then I have to worry about 1, 2, 3, 4 forces, and 2 of them are unknown. So I think we should take the sum of the moments about point A here. So we'll say sum of the moments about point A, and this should make it real easy. So I know that this is 10 feet away, 10 feet. So this would be 10 feet times dx. I don't need another parentheses there. 10 times dx. And I'm going to assume that counterclockwise, there we go, counterclockwise is a positive moment. So in reality, I'm going to say that this is, well, I've stumbled into something that we discussed in a previous video, but I'm going to assume that moments are positive in the direction they're drawn. So dx would cause this whole thing about point A, right? If I draw a moment arm from point A to point D, this will cause it to rotate that way. So I'm going to say it's positive in that direction. So 10 dx plus 12b, 12b, we'll put some of those in there. I'll do that in red just to be extra clear. 12b plus 24c. Remember that was another 12. 12 equals 0. 24 times c. So let's grab out our handy dandy calculator. From this, the sum of the moments equation, we can say that dx equals, do some algebra real quick, 12 times 10 plus 24 times 10. That divided by 10 equals 36. So dx equals minus 36. Equals minus 36k. K, when you talk about forces with a k on the end, it's just shorthand for 1,000. So this is 10,000 pounds. So this would be 36,000 pounds, opposite the direction we showed it. Some professors will prefer you, if you guessed the wrong direction at the beginning, to actually draw your force the other way. So some would actually tell you, go back to your free body diagram and redraw d of x in the correct direction. I don't. Some professors don't. It's more work, so we're not going to do it right now. There we go. So we have d of x. So now that should give us RA pretty easily. So that'll say that RA, we have minus 36 plus 36 equals 0. So this will tell us that RA equals 36k. And down here, back to this one, we know dy has to be the sum of all of these. So I can do mental math, that's 25. So we know that'll tell us that dy equals 25k. So, cool. Now we go back here, we can redefine this problem. Or not redefine, but we have all of the information that we need now for this problem. So we know that there's a force here, it's 25k. We know there's a force going that way, that's 36k. And we know there's a force going this way, it's also 36k. Cool. Now we can pick these apart at the joints. So I want to, we'll solve as many of these as we have time for. We might be able to get through all of them by 6 o'clock. But let's start. Oh, where do you guys, yeah, this would be a good question. Where do you guys think would be a good joint to start at, right? If I want to figure out all of the, if I want to figure out all of the, if I want to figure out the forces in all of the members for this structure, I want to do it in the least number of steps possible, right? I don't want to do extra work for myself. The more knowns that we can generate from the start, the easier our task's going to be. So, that being said, does anyone have any bright ideas as to where we might want to start this problem? Or start step, what is this? Step 3 of this problem. Right, so I said separate, oh no, separate the joints. So where we might want to start step 2. Any takers? point E. This one here. All right. We can start there. Does anyone else have an option? We'll do it starting at there and at another one. But you probably tell by my tone of voice that I don't want to start there. Yeah, makes sense. Yeah, no, that would make sense. Anyone else have a suggestion of where they'd like to start? Point D? I think point D is a pretty good option. But for Josh, we'll start at point E. And we'll do that, if not to prove a point, just because why not? So, point E. Point E. So, point E, we knew had a joint coming, or a member coming in this way, in that way, in this way, and in that way. So, point E, we'll do this loosey-goosey. Force there, force there, force there, force there. Draw our quick and dirty free body diagram. This is X, this is Y. And got 1, 2, 3. Oh dear. 4. That points to the point. What should we label these? I'm gonna call this one Jeff. Call this one Bob. This one can be Clarence. And this one can be Jill. So, let's do our sums of forces in X and Y. I'm going to assume that we know all of the angles for all of these things. If you go back to the problem description, right, you can do the trig. I don't want to do the trig, so I'm not going to do the trig, but those angles are all known. So, let's see. We have the sum of the forces in the X direction equals 0. So, this is going to be Jeff times, what would that be? Oh my gosh. Oh boy. We're going to switch to a finer line here. Jeff times the cosine of angle Jeff plus Bob times the cosine of angle Bob minus Jill times the cosine of angle Jill equals 0. All right, seems like a decent equation. Now we'll do sum of the forces in Y equals 0. So this is going to be Jeff times the sine of angle Jeff. Suppose I should put an F on there. Jill. I shouldn't have named these people names. I should have named these easier names to spell out. Jeff times, minus the sine, right? Because it's going in the negative Y direction. Plus Bob times the sine of angle Bob. Plus Clarence. Plus Jill times the sine of angle Jill. Equals 0. So, while these are perfectly valid, perfectly good statics equations, you know, later on, after we solve some other joints, they'll be useful. Right now, they're not very useful to us because we don't have any knowns currently. So right now, we have 1, 2, 3, 4 unknowns still. And that, well, frankly, doesn't do us much good. Later on, when we come back to this point, we'll be able to fill in all the unknowns, but for now, that is annoying. So, let's start at point D. That sounds fun to me. So, point D, back to this size. Point D. I'm going to go ahead and just draw everything directly onto my free body diagram here. That way I don't have to do it twice. So, at point D, we've got a reaction force. We've got a 25K force there. We've got another reaction force. That one was, what, 36K? Is that what we said? I believe so, 36K. And then we have two other forces. So we've got some tension force. I'm going to just call it F1. And some other tension or compression, could be either one, force. Actually, I drew those both as compression, so I guess I should call them both compressive forces. Call this force 2. And again, there's some angle theta here that if someone wants to calculate while we're solving through this, I think it's a 3, 4, 5 triangle. So actually 10, not quite a 3, 4, 5 triangle, but we can do it with fractions. So now let's do our statics. So sum of the forces in X equals 0. So that's minus 36 plus, oh, I said minus F2. That'll be cosine theta equals 0. And cosine theta here is equal to, what's that going to be? 10 squared plus 12 squared. Oh no, it'd just be 10 over 24, right? Yeah, 10 over 24. 10 over, oh, not 24. I did that wrong. That should be 24 over whatever 100 plus 24 squared is, right? Because this is our hypotenuse, this is our adjacent side. There we go. So from that, I now know what F is. Yay, because there's only one unknown. Let's do the sum of the forces in Y equals 0. So I've got 25 plus F1 plus, oh wait, hold on. Did I take care of my negatives properly? I did not. So this is actually going to be F2 equals minus 36 over cosine theta. And the easiest thing to do when you're doing methods of joints, or really any statics problem, is just going too quickly that you forget some positives and negatives. But good thing I caught it. Otherwise, that would have been slightly on the embarrassing side. So if we've got F1 here, then we'll say plus F2 sine theta now equals 0. And that means if we want to solve for F1, we can. I'm going to leave it symbolic for now, but we know what all the numbers are. So we can do F1 equals F2 sine theta minus 25. Cool. So now we have two known forces. So if we go back to our initial problem, we now know what this force is. That was F1. And we know what this force is. That's F2. Which means that if we were to then solve point E, now we have one known already taken care of. So then it makes it a little easier. We only have 3 unknowns that we have to worry about when we're solving these equations. We'll still have to do all the equations, potentially, but it now makes it a little bit easier, a little less algebra to solve for. There's technically no wrong answer on where to start. There's just better places to start that give you more information. So going forward here, let's see. Let's just put some numbers on there. 100 plus, oh, delete, plus 24 squared is that. Square root of that, probably 26. That's good enough. So if we do 24 over 26 times, what was that? Oh, wrong direction. Times 36. Oh, we want 36 over that. So 39. Good. That's a nice, easy round number. So F2 equals minus 39. So let's do 10 over 26 times 39. That minus 25. Oh, that should be, so that's negative. So that'd be a plus minus 25. Plus 25 is 40. So F1 equals minus 40. Coolio. So now we know that in this member here, we have a compression of 40K. And in this member here, we have a compression of 39K. And we could continue from there. You don't have to directly go to the next points, right? I think the next one I would go for, and actually probably the one I would start with, would be point C. Point C, we don't even technically need our external forces for point C, right? Because we got one direction this way, and then there's only one force that can even hold, that can even take up an x direction force. So we already know what the these two, we know the forces in these two members right off the bat without even needing to do our external statics. But yeah, so that would mean we know D right off. So we did D as our first point. Then we could do C as our second point. And now, if we want to do E from there, now we have two knowns already. So that'd be pretty sweet. We could also do point, I would say next after doing C, I'd probably do B, because then we know what the force is within this member. And this is just, these are all right angles. So we know that this one has got to be equal to that one. And we know that this one, right, this member has to take up all of the load in the y direction. So we know that one has to be 10K. So by doing D, C, and B first, now when we solve for E, we only actually have one unknown, which is just this member here. And we could see that, oh, sweet. Now, because I did C, D, B, and E, well, now I don't even have to do the statics for point A, because I know the force in this member. I know it in this member. I know that one from doing C. I know this one from doing B. And I know this one from doing E. So we've solved by taking apart the whole thing at the joints. We have, let's go back to here. So we first determined the equilibrium for the whole structure. We took it apart at the joints. We did statics on each joint progressively. I suppose I should add a progressively. Oh, that, I'm not going to write that out. That's that's too much to cram into there. And then we walked through the structure until we found the solution. So eventually, for harder, potentially more difficult statics problems or that you might need to use methods of joints for, you eventually start to get a feel for what you actually want to, what points you actually want to work into solving. So for a structure like this, well, I know, okay, this one only has 3 forces on it, so those are automatically things I can know. This one only has 3 forces on it, those are automatically things I know. So then I might say, well, I now know what the y direction is for each of these. And this would still have 2 unknowns because we don't know the x direction, so maybe I wouldn't choose that point next. But then I could go here and I say, okay, now this is a known force. So I get those 2 for free. And then the last one here is piece of cake. You also are likely to have problems where you only care about one member. So, all right, on the chassis, if I want to figure out if the firewall is strong enough, I really only care about the top member on the back of the firewall. Or let's say that we want to figure out what size we need that top member to be. Well, I don't have to solve, I don't even need to do the statics for anything else. I just need to figure out how do I work myself to these 2 points at the top. So, I think I have well and truly gone over time. Yeah, 6:05. So we'll stop there for today. I had another example we might go through next time, but I think I'll want to jump straight to the methods of sections. But that means we can cross off methods of joints for today, and next time we'll continue to work through our intermediate statics.